Hi, everyone. So this is the extra fun part of the night. I mean, the food's pretty decent, but it's the extra fun part of the night because we get to give gifts and money to people. So, at first, we're going to be giving the Feynman prizes. There's a prize in experiment, a prize in theory. They're given for people who have created exceptional advances in nanotechnology. We've been giving these out since 1993. There are 4 former Feynman Prize winners in the room right now, so you're all in good company. And now I'm going to put on my glasses. So they're officially for researchers whose recent work has most advanced the achievement of Feynman's goal for nanotechnology. So I expect most of you have heard of Richard Feynman. He never got a Feynman Prize because it was named after he was gone. So, and that's for the contributions toward atomically precise products through the use of molecular machine systems. And there's a former Feynman Prize winner who also happens to be a Nobel laureate in molecular machines. And so I'd like to welcome Sir Fraser up here to talk about this year's Feynman Prize winners.
All right. Well, good evening, everyone. So I'm going to start off with the Feynman Prize in Theory. And this prize is going to Professor Julie Galli, Professor of Electronic Structure and in the Institute of Molecular Engineering at the University of Chicago, and also holds a position as a senior scientist at Argonne's National Laboratory. And the prize has been awarded for the contributions by Professor Galli to devising molecularly precise products through the use of molecular machines. And they have been these contributions threefold. First, the invention of novel theoretical and computational methods to predict and design from first principles the structural, vibrational, and electronic properties of nanostructured materials. Secondly, the methods pioneered by Professor Galli include linear scaling algorithms for electronic structure calculations based on density functional theory. Next, a novel formulation of many body perturbation systems enabling accurate and efficient calculations of emission and optical spectra of heterogeneous nanostructures and solids, nanostructural solids, and molecules. And then also for the development of innovative strategies and techniques to broaden the scope and applicability of ab initio molecular dynamics and of methods traditionally used in solid-state physics to nanostructure or to nanoscience in general and nanotechnology. Professor Galli has also studied systems at the nanoscale in the focus, or with the focus, on semiconducting nanoparticles and carbon-based systems. She has, moreover, identified the key influence of surface morphology and functionalities of nanoparticles pioneering the field at a time when most of the scientific community was only focused on size effects and quantum confinement. I invite you, Professor Galley, to come up and receive the Theory Prize, the Feynman Prize.
Julia, a little.
Okay.
Oh, we're doing another. Okay.
Yeah, all together.
Sorry.
Without it.
With or without?
Oh, yeah.
Yeah.
All right, let's get 8, 3, 2, 1. Also 3, 2, 1. And a big smile finally. 3, 2, 1.
All right. Thank you very much.
Let us know a little about
Yeah.
your work.
Thank you very much. And I'm very honored, to be awarded this prize. And I would like to thank you, the Foresight Institute, for, the award. And I don't think this is a secret. So I would also like to thank Bill Goddard from Caltech for nominating me. Bill has been a supporter of my work and my group's work since the early days. I've been working in computer simulation of nanostructure and nanostructure material for a long time, almost 20 years. And you are as good as the students and postdoc that you can convince to work with you. So I've been really, really fortunate to have many students and postdocs to work with me, enthusiastic. And by the way, I'm also looking for postdocs, so please apply. And so when we started looking at nanostructure with computer simulation, and we wanted to look at the effect of surfaces, and at that time I was in Livermore using first principle simulation. I remember we submitted a proposal which was promptly refused. And we were told, no, surfaces, what is that? Surfaces of nanostructure. And so the reason why I'm saying this is that it's really important. There are many young people in the room to persevere and if you have ideas and if you think that things are important, just go for them. And if your proposals are refused, it's fine. One day they will be accepted, and don't listen to the people onto the bad referees report ever. So over the years, starting from refused proposal and all that, we built quite a bit of tools to do computer simulation of nanostructure, which have come to the point now where we can really make prediction. And I've been very fortunate to work with many experimentalists, and our work cannot be successful without a strong collaboration with experimentalists that we have been very fortunate to have during the years, and we still have. And thanks again for this amazing awards, and I hope you all enjoyed your evening. Thank you very much.
There's a lot of stuff up here. All right. So there's no guessing. The second prize, of course, is the Feynman Prize for experimental work. And that goes to Professor Liu Lu Chen from Caltech. She has made major contributions to molecular robotics, self-assembly of DNA nanostructures, and biochemical circuits. She has pushed the frontiers of molecular robots by developing DNA robots that explore DNA surfaces autonomously at the nanoscale level, picking up cargo molecules and delivering them to a designed location. This work demonstrates the importance of simple algorithms and modular building blocks in molecular robots, and enables the future development of general-purpose molecular robots. She has also pioneered the investigation of DNA tilings for creating nanostructures at the micrometer scale with nanometer resolution. Furthermore, she has developed a framework for programming DNA tilings. She has also developed a hierarchical strategy that allows DNA nanostructures with increasing size and arbitrary patterns to be created using a small and constant set of unique DNA strands. These two complementary approaches increase the complexity of the structural components and patterns used to create artificial molecular machines. Dr. Chen, her work is rigorous, creative, and inspiring. Although still at an early age in her career, she is already a recognized leader and rising star in the fields of DNA, nanotechnology, and molecular engineering. Fields that are anticipated to revolutionize many other research areas, including chemistry, medicine, and material science. I invite you, Professor Chen, to come up and receive the Feynman Prize for Experimental Studies.
Okay, so thank you very much. Is that good?
You can just put this here, but don't walk away.
Okay. So I feel really very honored to get this award. Especially I like this name. I like Feynman, I like nanotechnology. What could be a better name? So thank you for that. Well, the goal of my career is essentially I want to be able to develop programmable molecular machines, eventually approaching the sophistication of the natural ones. And I hope to be able to build the components, every single components from scratch, so that everyone can write their own molecular apps. And the hope is maybe that would allow all of us to explore the really large or sometimes even infinite programming space of chemistry and materials and medicine and et cetera. So that's a really big dream, but I know many of you might share a similar dream here, so that's particularly a great thing to be here today. But it's a pretty challenging and long-term goal. So I feel that there's two things being important in my research. One thing is that I would like to take inspiration from biology, which presents the best examples of what molecules are naturally good at doing. And I would also like to borrow the concepts and tools from computer science because that presents the most successful examples of engineering in human history. So that's kind of like the theme of my lab. More specifically speaking, we try to start by developing simple and modular molecular building blocks and then try to understand their behaviors as systems, and then finally try to create abstractions and programming languages to help us to more efficiently design those molecular systems. But of course, because it's such a long journey, even though I believe nature conceives all the power and truth and beauty that we seek, but including the kind of fundamental principles about how molecules could sense and compute and actuate. But this journey must really be lit by the fire in our own hearts. And because of that, I must thank Greg Tikamirov. He's the first member of my lab, and he brought the fire into my lab, and then he passed on to the other graduate students and postdocs, and they allowed me to be on this journey with them. And that's the only reason that we were able to make just small steps toward the long-term dream. So thank you, Greg, for being here today. And I also want to thank my husband, Eric Winfrey. So he was actually the winner of this award in 2006. And as you can tell, well, I don't know, I should be happy about it. He's pretty much around at least 10 years ahead of me for everything. That's a good thing because then I continue to learn from him, so that's great. And I think finally, I just want to thank the Foresight Institute because you create such a special environment to bring people together with diverse backgrounds, but who share a very similar dream, to come here to inspire each other. And I think that's the only way a dream could grow into reality. Thank you.
Thank you, Lulu and Julia. What's that?
She took the clip with her.
Oh, well, she's just right over there. You get it back. And finally, I say finally, so you better get dessert soon. The Distinguished Student Award. So the Distinguished Student Award we've been awarding since 1997. It's to college grads or undergrads whose work is notable in the field of nanotechnology. There are 3 individuals who have been funding this award for a number of years. One of them is Jim Von Eyre, and one of them is James Ellenbogen, and one of them we're lucky enough to have tonight here is Ravi Pandya. So Ravi, come on up.
Just a little one. And you still have to talk into the podium like this video. There you go.
All right. Well, yeah, thanks, Steve. So it's been a real pleasure for all of us to be able to fund this prize every year, to really see the outstanding work these students have done, and then to see the work that they go on to do in the future in their careers. It's been really impressive and really rewarding. So the winner this year is notable for their work in liquid crystal elastomers, LCEs. And they and their lab introduced magnetic field-guided encoding of highly controlled molecular anisotropy into 3D liquid crystalline elastomer microstructures, capable of displaying unique multi-responsive shape-changing behaviors. And this is of note because the range of allowed deformation modes that's currently described for microstructures is very limited. This candidate and their lab mates have shown that by polymerizing this molded prepolymer and patterned magnetic fields, they can code any desired uniform messagen or liquid crystal orientation into the desired LCE. And the resulting platform can be harnessed into a wide variety of applications, including switchable adhesion, information encryption, autonomous antennae, energy harvesting, soft robotics, smart buildings, and other things. This candidate defended their PhD thesis in April of this year, but is already an author on 9 publications with a total of over 500 citations. They've been a postdoc at Harvard in the Biomineralization Biomimetics Lab under Professor Joanna Eisenberg, and are leaving this lab this month and moving to the Shapiro Lab at Caltech under Professor Michael Shapiro, who will be their advisor. I'm very pleased to present the 2019 Distinguished Student Award to Yuxing Yao. Yeah, so if you have anything you want to say about your work, you're welcome to do that now.
Oh, really? Wow. Yeah, we're just getting to know. Wow, you know what? It's just a huge surprise. Probably a lot of people have seen it. I was actually taking off my blazer. I was like, okay, finally tonight is over. But I don't know, actually it's over in this, the best way I can ever imagine. Actually, it's kind of funny because right before this dinner, some friends and I were just talking about this student award. We're like, whoever gets the award should buy, a drink or buy whatever, a milk tea. I just checked, there's a milk tea place around. But anyway, oh wow. I need to check this one first, probably. But yeah, I really appreciate it. So for me, I'm just super honored to be here, and I think for my graduate study, I started to work on it's just like a molecular level anisotropy to build in polymeric materials to control the mechanical deformations. And we're trying to design it in a biomimetic way. And then later on, when I'm choosing the way to pursue for my postdoc, I was like, okay, we're learning bio to design materials. Why don't we just learn more about biology, especially how they control themselves in different, for example, genetic circuits. So that's why I try to learn more about the synthetic biology. That's why I made a switch to go to Mikhail Shapiro's lab in Caltech. So hopefully this switch will be, fruitful to some extent. So thank you again for the great surprise. Thank you.
Congratulations.
Thank you so much.
So that's it. Obviously, Marcia may have a few logistical things to say. What I want to say, again, is thank you all so much for coming. Thank you again you're going to go out, you're going to prosper. Some of these ideas are going to come to fruition. You're going to heat up the room just as much with your brain action as this room today. That's how you'll know. Thank you all so much.
All I can say is thank you again and party on.